Welcome to Botronix Labs Intermediate Robotics, Module 3. In this special project, we're taking robotics to the next level by transforming our previous builds into a single, powerful platform. We've combined the robot tank, now serving as a mobile base after removing the IR sensor, with the 4DOF robot arm from the Fundamentals course, stacking them together to create a fully integrated mobile robotic system. This new robot can drive around, grab, and manipulate objects, unlocking a whole new world of possibilities for your robotics journey. But that's not all. With our advanced BLE feature, you can seamlessly switch between controlling the tank and the robot arm using a single controller. This means you can mobilize your robot, then instantly switch modes to operate the arm and grab items, all wirelessly, all in one project. For this project, you'll need 3 Raspberry Pi Pico W boards, 1 for the controller, 1 for the tank base, and 1 for the robot arm. A WaveShare 1.3-inch Pico LCD display with joystick and buttons for the controller. 4 servo motors for the 4DOF robot arm, base, shoulder, elbow, and gripper. An HW354 dual DC motor driver for the tank base. 2 DC geared motors for tank movement. A blue LED BLE indicator for the tank. A yellow LED BLE indicator for the arm. 2 330 ohm resistors. Power supply, 2 18,650 batteries, 2 DC-DC boosters, or USB power banks. 1 slide switch. Jumper wires, breadboard, and connectors. 3D printed enclosures and mounting hardware for stacking the arm on the tank. Let's start with the design overview for our transformed robot arm tank project. On the hardware side, we've made some key changes to integrate the 2 previous projects. For the robot tank, we've removed the IR sensor to mount the arm. For the robot arm, we've upgraded the controller board to a Raspberry Pi Pico W, enabling wireless BLE communication. We then physically stack the robot arm on top of the tank, connecting both with their own dedicated Pico W boards. The tank serves as a mobile base, while the arm provides 4 degrees of freedom for grabbing and manipulating objects. This integration allows us to create a single, mobile robot that can both move and interact with its environment. On the software side, the real innovation is in the BLE communication architecture. The controller Pico W acts as a BLE central device, while both the tank and the arm act as separate BLE servers, peripherals, each advertising a unique name and UUID. The controller can scan for both devices, display their status, and connect to either one at a time. With a simple button press, you can switch the controller's BLE connection from the tank to the arm, or vice versa, without needing to restart or repair. This BLE switching is handled in software by disconnecting from the current server and connecting to the other, updating the GUI and internal state so you always know which robot you're controlling. This modular design makes it easy to expand or adapt the system for more robots or new features in the future. Now, let's dive into the BLE Service Architecture that makes multi-device control possible. Each robot, the tank and the arm, acts as a separate BLE server, advertising its own unique name and a dedicated set of BLE UART service UUIDs. For example, the tank might use a UUID starting with 6E4000, while the arm uses a different one, like 7E4000. This separation ensures that the controller can easily distinguish between the 2 devices during scanning. When the controller Pico W scans for BLE devices, it filters the results by both advertised name and UUID. This way, it only shows or connects to the intended robots, even if there are other BLE devices nearby. Once a connection is established, the controller communicates with the selected robot using the BLE UART service, sending commands and receiving feedback in real time. The controller's software keeps track of which device is currently connected, and with a button press, it can disconnect from one and connect to the other, updating the user interface accordingly. This architecture not only allows seamless switching between the tank and the arm, but also lays the groundwork for scaling up to even more robots or peripherals in the future. By using unique names and UUIDs, you can expand your robotic fleet and control them all from a single, smart controller. Let's look at the BLE server running on the robot tank. The tank's Pico W is programmed to act as a BLE peripheral, advertising a unique name and UUID so the controller can find it easily. Once connected, the tank listens for simple movement commands: forward, backward, left, right, and stop, sent over the BLE UART service. The code is organized using classes for modularity. The main class handles BLE setup, command parsing, and motor control. When a command is received, the tank's motors respond instantly. A blue LED on the tank acts as a BLE status indicator. It blinks while waiting for a connection and turns solid when connected, giving you clear visual feedback. Now, let's move to the robot arm. The arm's Pico W also acts as a BLE peripheral, but with its own unique name and UUID. The software uses an object-oriented approach, with a dedicated class to abstract servo control for each joint: base, shoulder, elbow, and gripper. Commands are sent over BLE UART in a simple format, like B90 to set the base to 90 degrees, or G0 to open the gripper. The BLE server parses these commands and updates the servos accordingly. A yellow LED on the arm provides BLE connection feedback, lighting up when the arm is connected to the controller. This modular BLE server design makes it easy to add more joints or features in the future and ensures smooth, real-time control of the robot arm from the central controller. The real magic happens in the controller's software. The controller Pico W acts as a BLE central device, scanning for both the tank and arm servers. The user interface, displayed on the LCD, shows which robot is currently selected, connection status, and available controls. You can use button A to toggle between the tank and the arm. Button B connects, button X disconnects, and button Y, combined with the joystick, lets you incrementally control each servo on the arm. Pressing Y alone resets all servos, and the control button toggles the gripper open or closed. The GUI updates in real time, highlighting active buttons, showing directional arrows, and providing feedback from the robots. Internally, the controller tracks which device is connected and manages BLE switching by disconnecting from one server and connecting to the other, updating the interface and internal state so you always know which robot you're controlling. This flexible design not only makes the system easy to use, but also sets the stage for future expansion, like adding more robots or new control modes. Now it's time to see everything in action. First, power on all three devices: the controller, the tank, and the robot arm. The controller's LCD will show the available robots and their connection status. Start by connecting to the robot arm. The LCD updates to show you're now controlling the arm, and the yellow LED on the arm lights up. Use the joystick and button Y to move each servo joint incrementally: base, shoulder, elbow, and gripper. Pressing Y alone resets all servos to their default positions, and pressing control toggles the gripper open or closed. Next, press button A on the controller to switch modes. The controller will disconnect from the arm and connect to the tank. Use the joystick to drive the tank forward, backward, left, and right. Notice how the blue LED on the tank lights up solid when connected, giving you instant feedback. You can switch back and forth between the tank and the arm at any time, with the controller handling all the BLE connections and GUI updates seamlessly. This demo shows how you can mobilize your robot, then instantly switch to manipulation mode to grab or move objects, all with a single wireless controller. With this project, you've learned how to combine two robotics platforms into one powerful, mobile, and interactive system. You've explored advanced BLE communication, modular OP design, and real-time GUI feedback, all skills that are essential for building scalable, flexible robotics projects. This architecture makes it easy to add more robots or new features in the future and opens the door to even more advanced projects, like autonomous navigation or remote control over Wi-Fi. Thanks for following along with Botronix Labs. If you enjoyed this module, be sure to check out our next course, where we'll add even more intelligence and connectivity to your robots. Happy building!